How's everyone doing? My name is Dr. A.J. Kumar, PhD. And today we're talking about a variety of things. I've split it up into sort of three sections, but the first thing is sort of very abstract, and we're going to get more and more specific. The first thing is truth versus reality, and this ties into some mathematical points I want to make. So, I don't remember who told me this, but there are three fundamental questions in philosophy. Now, disclaimer, I don't know anything about philosophy, so don't get mad at me. The first question, what is true? Second question, what is real? Third question, what is good? And I analogize these with a map, a territory, and a compass. And it's important to mention, to keep in mind that these are three different questions. That's what's important, is to recognize that these are three different things. Reality is sort of the real concrete constraints of the world that we live in. The map is sort of our model, which is truth, which is our model for how do we navigate reality. And then what is good tells us what we should and shouldn't do, and that's our compass. That tells us where to go. And what's really important is recognizing that these are three different ideas, and three different ideas. That's a fun exercise. Ask some people to explain the difference between these three concepts: truth, reality, and good versus bad. Truth, reality, and virtue. Have them explain the difference between them. And a lot of people don't realize that two of them are different things, and which two they've fused together is really interesting. Anyway, one idea I'm kind of toying with is this idea of pairwise opacity. And this is something you get from concurrent programming, which is you have one process that sits over here and another process that sits over here, and they can't look into each other's memory, but they can send each other messages. And that's the idea of science, which firmly lies in the domain of truth, which is science sort of does message passing with reality. It asks reality questions in the form of experiments, and then science builds mathematical models that try to model the way reality works, but it's important to not confuse those models with reality. Newton's law of gravity is a different thing than gravity. That's really important. And this is going to tie into some mathematical points I'm making. So before I go on, I'm borrowing a lot of the examples and ideas here from various playlists that Wildberger has, so I'm not trying to plagiarize anything, but that's where a lot of this comes from. And I'm not proving anything rigorously, I'm just trying to explain what's going on and untie the knots that people have in their head. And my main point, or maybe not a main point, overarching point, is that mathematics is true, but it is not real. This implies that there will be hidden trade-offs in mathematics, which is, do you have truth that is more coherent, or something that more closely resembles reality? In some way. Now, generally, these trade-offs come in the form of, here's your first option. Sorry about my handwriting. Option 1, mathematics is coherent, and it makes sense, but it's counterintuitive. Let me zoom out. Option number 2, obvious facts about reality are true in mathematics at the cost of mathematics becoming incoherent and nonsensical down the line. And in general, it's better to choose option 1. But sometimes you don't even realize that this is a trade-off you're making. When you choose one side of the when you choose one fork in the road, you might not see the other fork. So the fork would be both of the things, one prong in the fork. You might not even see that there's another prong. But if you do see the two prongs, and one of them is one of them you buy. Let me keep going, and I'll explain more. So, in other words, option 1, you accept some small upfront complexity in exchange for a simpler story down the line that is more coherent and simple. Number 2, you buy some artificial simplicity up front at the cost of angry dragon problems down the line. So I have some examples here. Oh, and I wanted to say, These trade-offs are everywhere. It's usually not obvious that you're making one of these choices at the time that you make it. And there's a really good example for yellow, and let me just write it. This is in computing, which is floating point arithmetic. That's really the best example. And generally, it's better to choose option 1. So examples of where you buy a little bit, you take some upfront complexity in exchange for things becoming simpler down the line. So projective geometry is a good example of that, and we're going to talk about that a little bit in a few videos. Complex numbers. So if you know a little bit of complex numbers, you'll understand what I mean. Property-based reasoning. Now what I mean, abstract reasoning, or algebra is another, not modern or abstract algebra, I mean like algebra you learn in high school. That you buy some, you take a little bit of complexity, which is instead of talking about numbers, you talk about abstract symbols, and that ends up making things simpler down the line. And then some examples of where you buy some simplicity that's artificial at the cost of angry dragon problems, which is sprawling, uncontrollable complexity. I call this the cell wall problem. So a cell wall is a mechanism that a cell uses to push entropy outside of the cell wall. And then so it can maintain a relatively ordered system inside and then pushes the unused energy outside the cell, the excess energy. And this is a cell wall problem, which is if you do that too much, if you push out entropy that you're not supposed to push out, meaning if there's some complexity or some energy that you need inside the cell, and you push it out, it's going to come back and bite you. Those are called, I call them angry dragon problems, or the cell wall paradox. Maybe would be another term, cell wall paradox. So examples of this would be irrational numbers, stacking infinite processes on top of each other, and I did a really good example of this in the third WFC video. The idea that you can measure these things called angles. Then you have the idea of limits. This is the big one in math, is these idea of limits, and then floating point arithmetic, which I just wrote down. So I'm going to give two specific examples. I don't know why I wrote larger. I guess the areas of polygons one is larger. So a good specific example is this premise. So here is a circle of radius 1, and I drew a line with slope equal to 1 that goes through, that's a diameter of the circle, and there are these 2 points where the line appears to intersect the circle. And so the question is, what are the points of intersection? Well, in irrational or traditional geometry, well, here are the coordinates. A is equal to 1/2 of the square root of 2, 1/2 the square root of 2, and B is equal to just the flip of that, minus 1/2 the square root of 2 and minus 1/2 the square root of 2, and, you know, draw out a picture using geometry to convince yourself of that. And in rational geometry, where we insist that, I don't want to say insist that everything is rational, but are very careful about the types of irrationalities we're willing to put up with. That's maybe a better way to think about it. We say the line does not intersect the circle, which is kind of bizarre, but actually this ends up being a little bit easier. So in irrational geometry, you have this geometrically obvious fact. The diameter of the circle, any diameter of a circle, will intersect the circle in exactly 2 points. This is true, but in exchange you have to accept points with irrational coordinates. And that introduces all sorts of crazy problems. The real numbers introduce all sorts of crazy problems because they don't actually really make a whole lot of sense. And Weilberger talks about that a lot more. And all you have to do, by the way, to convince me that real numbers make sense, and that all the claims that people make about real numbers, about how, well, you can't do an infinite process, but you can do it to arbitrary depth. Okay. All I want you to do is take the decimal expansion for pi and give me the 10 to the 81st digit. Okay, that's all you have to do. Compute 10 to the 81 digits of pi and tell me what the 10 to the 81st digit of pi is, and I will accept your irrational number. Actually, you have to give me the first 10 to the 81 digits. So this is a 1 with 81 zeros after it.